In the previous lesson, we talked about how the Pearson correlation should only really be calculated on continuous data, and also how outliers can kind of distort the picture and mislead us. The examples that I've used to illustrate this point was Ascom's quartet, and these four charts illustrated how very different patterns in the data can actually give you very, very similar descriptive statistics if you're not careful. What I want to show you now is how this isn't really just a hypothetical example. We can also see something similar happening in our housing data set when we don't apply the right tools to the right kind of data and aren't careful with our interpretations. Remember how a correlation of 0.9 or 1 is meant to look like? You'd expect to see a chart that kind of looks like this, where the data points almost form a straight line. Looking at our correlation matrix, we've actually got a number here, a very high number, 0.91, as the correlation between RAD, our access to radial highways, and our tax feature. So given our expectation of what a high correlation between two variables would look like, let's visualize this relationship and see what we get. I'm actually going to copy this cell here with our joint plot from Seaborn, and then I'm going to paste it in here. Move the cell down, and then what I'm going to do is I'm going to change the references from distance and nitrous oxide to tax and RAD. And for the color, I'm going to go with, I don't know, maybe dark red, and then hit Shift Enter. Voila. This is what we get. Now, this picture is probably not what we would have expected to see had we just looked at the correlation. But we've said before that this very high correlation that we have between these two variables is a result of the fact that this data is not continuous and the fact that there are these big outliers in the top right corner that are driving this correlation. One thing that's actually very interesting to do as an exercise is to plot the linear regression onto this chart and see how it's affected by the data here. So let's see what would happen if we ran a linear regression between these two features. Now, previously, we've run our regressions separately using the scikit-learn module, and we've plotted our best fit lines on a matplotlib chart. Let me show you a shortcut on how you can use Seaborn to do this very, very quickly. So if I come down here, and in this cell, I'm going to make use of a function called lmplot. So SNS dot lmplot, parentheses, and then x is going to be our tax, and y is going to be RAD. And for the data that we're going to feed in, the data keyword argument is going to be our data frame. So it's going to be data. Data equals data, comma, size equals 7. So what this line of code is going to do, it's going to look in our data frame, which is this bit of Python code here, and it's going to look for a column called rad. And it's also going to look for a column called tax. The thing that might be a little bit confusing is this data equals data Python code. But this first part, data equals, is the keyword argument, and data here is the name of our Python data frame. So I'm going to add another line, plt.show, and hit Shift Enter. Voila. And just like that, we've plotted a linear regression between our two features on this chart. Seaborn has done a lot of work for us here, and I hope you're seeing just how useful this little Python module really is. Now let's interpret and make sense of what we're looking at on this chart. The data points in our top right corner are affecting the slope of our regression line significantly. It's like they're pulling up that regression line to make it steeper. And looking at this, you can see how a linear regression between rad and tax might not be such a good idea. because the regression line is kind of meant to represent the data a bit better, right? And here we're forcing this linear regression model onto a data set that's not really suited for it. Our computers will happily do this calculation, but we end up with a model that's perhaps not so useful to capture the true relationship between accessibility to highways and tax. But luckily, we're in the business of estimating house prices, right? So what we should actually be looking at is how our features relate to our target, namely our Boston property values. So coming down here, I want to give you another challenge. I want you to pause the video and run a few more scatter plots for data visualization. The first one should be between the number of rooms, RM, and our target. This is the price series in our data frame. Now you can either use matplotlib or Seaborn to accomplish this. I'll give you a few seconds to pause the video. Ready? Here's the solution. Now, I'm going to be very, very lazy, and I'm going to come up here and copy the code that I've previously written and paste it down here. And what I'm going to do is I'm going to change all the references from NOx and DIS to RM and TGT target. So data RM and data price for the correlations. And of course, I'm going to change the inputs to the scatter plot. For the color, I'm going to go with sky blue to differentiate it a little bit. And then I'll see RM versus price. And then for the correlation, of course, I'm going to go RM underscore TGT underscore core. And this is going to be RM, which is the median number of rooms. And in the Y label, it's going to be price. Property price in thousands. Let's see what we get. Voila. Now let me do the same thing with Seaborn. And you know what? I'm going to use lmplot to pull up the regression line as well. So sns.lmplot parentheses x equals rm, comma, y equals single quotes price, comma, data equals data, and I'm going to say size equals 7, plt dot show parentheses. Ta-da. Okay, so how do we interpret what we're seeing here? Well, the first thing is that our positive correlation of 0.7 approximately ties out really, really nicely with the relationship that we're seeing on the scatter plot. So this means that room size alone has a very, very clear relationship with our house price. And I think that's kind of neat to see. One of the other things that I find quite interesting when looking at this chart is that there almost seems to be like a ceiling on the property prices at the $50,000 mark, because there's a lot of data points that are on this line here. And I think that's quite curious, because it could be coincidence, but it might also have something to do with how the data was collected in the 1970s. But for the purposes of this tutorial, I'm not really going to dig into these kind of details. There's so much other stuff that I want to focus on. One of the things that you might already be thinking at this point is we've got like 13 variables, and there's just too many combinations to graph individually. We can't possibly copy and paste like our cells and our code to graph all these scatter plots individually, right? And yeah, we're not going to do that, because remember, we have to think like lazy programmers. And what would lazy programmers do? They would graph every single combination at once. And this is where Seaborn is going to come to the rescue once again. because Seaborn has a function called Pairplot, which will do just that. So SNS.pairplot, parentheses, and then as an argument, it needs our entire data frame. So SNS.pairplot, parentheses, data, plt.show, will create scatter plots between all our features and our target. But I hope you didn't type Shift-Enter just now and run this thing already, because there's something I want to show you before I execute this cell. I want to show you a little bit of Jupyter Notebook specific code, a little bit of Jupyter Notebook magic, if you will. Because the thing is, Pairplot actually has to do a lot of calculations, and it takes some time to run. And what I want to show you is how you can benchmark or time specific bits of code. People actually call this microbenchmarking because we're benchmarking a few lines of code. We're benchmarking an individual cell. And there's a magic command for Jupyter Notebook. And this command is %, time. And now I'm going to hit Shift-Enter to run this cell. Ready? Here we go. Now my computer has produced all these plots. Check it out. And because I've added that Jupyter Notebook magic code, I've got some additional information printed out here as well. This is showing me how long it took to run my code. Now, when you're running this at home, I don't know how long it'll take you. I don't know if it'll take you like 19 seconds, like it took me, or like 40 seconds, or maybe 5 seconds, depending on the kind of machine that you've got. But I think this is a really neat feature from Jupyter Notebook, because suppose you want to make a decision between two different types of algorithms or two different ways of running your code. Say if you've got something that takes a little bit longer and you're looking to like optimize it a little bit or do a horse race between two different algorithms, this timing capability of Jupyter Notebook can come in quite handy. So we've done this a little bit out of curiosity, and so that you can see that, you know, your computer didn't freeze up or whatever, because it took me some time as well to run this bit of code. But that said, this has some other practical applications as well. Another thing to know about Jupyter Notebook actually on this note is that up here in the right-hand corner, there's a little dot here that for me is currently not filled in. And when I hover over it, I can see it says kernel idle. This means that Jupyter Notebook is currently not doing anything. If I was to execute this cell again, during the execution, you could see that this dot is filled in and it says kernel busy. So this gives you an indication that at the moment, our Jupyter Notebook is doing a lot of work, and that even though it might look like there's nothing happening, our computer is actually working. This is another handy little thing to know about Jupyter Notebook. Now let's take a look at our output here. So what you can actually see here is kind of a cropped version or a zoomed out version of the actual size of this image. This image, in fact, here is a lot larger than what's being displayed. So we're kind of zoomed out. If you wanted to see the full size image, which I encourage you to try and do, what you can do is you can right click on this thing, click Save As, stick it in your Downloads folder as joint plot or what have you, and then in your Downloads folder, open it up and pull it up in your graphics program of choice. So I've got a Mac and I'm using Preview here, so I can go here and go to Actual Size. And here you see a zoomed in actual size 100% version of this image. Now, the other thing that you can actually do is you can open this image up in a new tab. So if I right click on this image and I'm using Firefox here, this will be different on Chrome or Safari or Internet Explorer, of course. But what you can easily do is you can do something like this, and then you don't have to download this image and dig it out of your downloads folder. So I think this is quite handy. Now I've got two tabs, one with the full-size version of the image and one with my notebook. So what we can see here is that we've got scatter plots for every single column in our data frame. So we've got price versus crime, price versus zone, price versus industry, price versus Chaz, price versus NOx or RM. And then we've also got LSTAT versus crime, LSTAT versus zone, LSTAT versus industry. But the really neat thing is that in the diagonal, down the middle, so this would be crime versus crime, we get a histogram. So this is the histogram for the ZN feature. This is the histogram for Indus. This is the histogram for Chaz, and so on. And down here, we've got the histogram for price. So the diagonal shows us the histograms, and everything else shows us a scatter plot. Scrolling down to the last row, namely the price row, we can check out for which features we can very, very clearly see a relationship between property prices and the feature. So here, this is crime and price. Going a bit to the right, we've got price and industry. And we can definitely picture some sort of relationship here, right? Going a bit further, we've got price and room size. This is the scatter plot that we've created earlier. And here there was definitely also a relationship. Going further, all the way to the right, we see this one here, price and LSTAT. Now again, this scatter plot is actually showing us a very, very clear relationship between these two things. It almost reminds me of pollution and distance in terms of its shape, right? But what is LSTAT? We haven't really talked about this feature before. So let's take a look at the description. So coming back to the Jupyter Notebook, to the top where we printed out the description, we see that for LSTAT, it's percentage lower status of the population. Now, this description might not be sort of the politically correct wording that people might use these days, but in a nutshell, this feature measures the socioeconomic background of people in the neighborhood. I actually wanted to get a little bit more detail on LSTAT, so I checked back with what it said in the original research paper to get a little bit more of a complete description. And what it says here is that by lower status, what the data is actually capturing are things like what percentage of people don't have a high school education, and what proportion of male workers are classified as laborers. So when I read this description, I immediately looked back at my correlation matrix, because what I wanted to check was the correlation between LSTAT and industry. So the proportion of industry in a neighborhood and the proportion of people who are classified as laborers or who don't have a high school education. And that correlation, it turns out, is 0.6. So it's both positive and fairly high. So reading this description, now all of a sudden this correlation made a whole lot more sense. And coming back to this scatter plot between LSTAT and house prices, is that what we can also clearly see is that the property prices tend to be lower in areas that have a high proportion of people who have no high school education or who work in factories. In other words, the property prices appear to be affected by the kind of people who live in the neighborhood. But we shouldn't jump to conclusions just yet. Our multivariable regression will tell us a lot more. But speaking of regression, and looking at these charts in the Pairplot, wouldn't it be nice to be able to plot a regression line onto all of these plots as well? I think that would make it a lot more clear, don't you think? Let's go back to our Jupyter Notebook and go down into the next cell, because SNS.pairplot parentheses data, comma, kind equals single quotes REG will show us that Seaborn will happily oblige if we add an extra argument to the powerful pairplot function. All we have to do is change the kind argument from scatter, which is the default. So pressing Shift Enter, we can see that kind equals scatter is the default for this function, and change that to regression, which has the code REG. Now, I know what this regression will look like because I've already run this code before, but the thing is, it will be colored in exactly the same way as our data points. So it'll be blue on blue, which won't be very, very helpful. We want to color our regression line in a little bit differently. And I want to do that now. I don't want to execute this code, wait 20 seconds, and then add more code, wait another 20 seconds. So I'm going to add another keyword argument here, and that's going to be the plot_kws keyword argument, plot_kws, and I'm going to set that equal to a dictionary. This is how we're going to add a splash of color to our regression line. A dictionary always has the curly braces, and then it has a key and a value. The key is going to be line_kws. And then the value comes after the colon. So what's the value that we're going to put here? It turns out it's actually going to be another dictionary. So we're going to have curly braces, and then another key, which is going to be color, and then a colon, and here's the value, cyan, which is going to be the color I'm going to use. So what we're looking at here now is a dictionary, color, colon, cyan, which is the value for another dictionary, which is the line_kws key. In other words, we've got a nested dictionary, a dictionary inside a dictionary. It's like the most boring version of the movie Inception, but this is how we're going to get a color for our regression line. All that's left to add is plt.show. And because I'm a very curious person, I'm also going to add the %% time Jupyter Notebook magic. Now I'm going to hit Shift Enter. Bum, 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 bum. What is happening? I should really get a coffee while this is running. There we go. Now it finished. How long did it take to run? 47 seconds. It's absolutely brutal. But let's take a look at what this looks like now. Again, we can see just how big this image is. It's about 2,500 pixels times 2,500 pixels. This is at 25%. At 100%, it looks more like this. With the help of our regression line on our chart, we can now also visually see the positive relationship between our industry variable and LSTAT. So we know the correlation was around 0.6, and now we can also see that borne out in the positively sloped regression line right here. And in the last row, we can see a regression line between each feature and our target variable individually. This is really neat because we can see if the slope is positive or negative, and it's basically doing a univariate regression 13 times. But the power of our analysis isn't going to come from looking at our regressions against the target in isolation. The power comes from combining all our explanatory variables and running a multivariable regression. Now, I have a feeling this air pollution themed cartoon reference is betraying my age a little bit. The point I'm trying to make is that we're going to combine all the explanatory power in our features to estimate our property prices in Boston. And our model of choice is called multivariable regression. And after we've done all that, we're going to evaluate our results and see if we can improve our model further. I'll see you in the next lessons.